So now that we've looked at properties of dot products, let's go through and let's just find some dot products. So we've got two vectors in R2 on number 24, and they're asking us to find a few things. A is asking us to find u dot v. So it's going to be -1 times 2 plus 2 times -2. So we're going to have -2 minus 4, which is going to give us a -6 for that dot product. B is asking us for v dot v. So we're going to have 2 times 2, which is 2 squared, plus -2 times -2, which is -2 squared. So we're going to have 4 plus 4, which is 8. C is asking us for the value of the magnitude of u quantity squared. So if we want to find the magnitude of u, it would be this. And when I square that, what's going to happen is that squared is going to undo that square root. So we're going to be left with -1 squared plus 2 squared, which is going to give us a 5. D is asking us for u dot v multiplied by v. So when we find a dot product, remember we find a scalar value. So this ends up being a scalar times a vector. So u dot v we found in the first problem, part A. So that was a -6. So now we have -6 times our vector of v to -2. So our vector is going to be -12, 12. And then E is going to be u dot 5v. So we could use the property 3 from above. 5 is a scalar value, so this is the same thing as 5 times u dot v. And we already know what u dot v is. We found that in part A. U dot v was a -6. So this is going to be 5 times a -6, which gives us a -30. So we can use those properties to make E a little bit easier. Dot products are used to help us find the angle between two vectors in space. So if we want to find the angle between two vectors, cosine of theta is equal to u dot v over the magnitude of u times the magnitude of v. So to figure out what theta is, we could take the inverse cosine of both sides. So I want to explore this a little bit. So when we talk about inverse cosine is always defined in the first and the second quadrant. So we're always going to get an angle between 0 and 180 degrees. Now that denominator consists of lengths or magnitudes or norms. So since we're taking the norm of u and the norm of v, we're always going to have a positive in the denominator. The sign of this is really going to come from what's going on in the top, that numerator. So if we know something about that dot product, then we know something about the angle before ever computing the angle. So if that dot product happens to be positive, that means we're going to have an acute angle. So the angle will be something between 0 and 90 degrees. So I'm going to write it this way. Now, if the dot product is negative, then that means this angle is going to live in quadrant 2. So we're going to have something between 90 degrees and 180 degrees. These should be strictly less than. Let me correct my notation here. Now, if that dot product is 0, then that means we have to have a 90-degree angle, because the inverse cosine of 0 is always going to end up being 90 degrees. Okay? Which means that these vectors would be orthogonal. So let's look at an example of how to apply that. And I'm going to use the last vectors we graphed in GeoGebra. So let's let U be 1, 1, 2 and V be negative 1, 3, 0. So to figure out what our angle is, find the angle between the two vectors. It's going to be the dot product divided by the product of the norms. So it's going to be negative 1 plus 3 plus 0 on top. The magnitude of V would be 1 squared plus 1 squared plus 2 squared. The magnitude, that's the magnitude of U. The magnitude of V would be negative 1 squared plus 3 squared plus 0 squared. So we know cosine of theta is equal to 2 over square root of 60. So theta is going to be the inverse cosine of that. I do want this in degrees. This textbook uses degrees primarily for angles. So make sure your mode on your calculator is in degree mode. And I got roughly 75 degrees. So if we were to go back to our picture in GeoGebra, here's a vector 1 and vector 2. And you can see that that's definitely going to be an acute angle between those two vectors. And that angle measured between here would end up being approximately 75 degrees. So that's how we use that formula. So there's just a little bit more talking about, like we talked about before, the sign of that dot product and whether our angle was positive, negative, based on the dot product, whether it was negative, positive, or 0, and what would happen to that angle. And they are using radians here instead of degrees, but most of the time in WebAssign it will want it in degrees. Just watch your notation there. We do have orthogonal vectors. If that dot product is equal to 0, that happens because of taking that inverse cosine, which we talked about. So let's do another one. Let's say we want to find the angle between these two vectors. You may want to pause the video and try this one on your own, and then come back and check your answer. So our dot product is going to be negative 6 plus 6 plus 0. So right away, I already know I'm going to have a 0 for the top. It doesn't matter what the bottom is. A vector, as long as it's not all zeros, will always have a length greater than 0. So you don't have to worry about dividing by zeros in these problems, is what I'm trying to say. 0 divided by any number is still going to be 0. But if we wanted to write this out, we could. So then the inverse cosine of 0 is going to give us 90 degrees, or we could say pi over 2. So that's your angle between those two vectors. Now we can use this idea of a dot product to tell us whether we have orthogonal vectors. We already said that u dot v has to be equal to 0 to be orthogonal. To be parallel, one vector has to be a scalar multiple of the other. So if the dot product's not 0, check for parallel. If one's a scalar multiple of the other, then they are parallel. If neither of those criteria happen, then the set of vectors would be neither. They're neither parallel nor perpendicular. So let's look at a couple of examples. If we were to look at 45, I'm going to start by finding the dot product. That's the easiest thing I think to see in that one. So if I find that dot product, 2 times 3 halves plus 18 times negative 1 over 6. So I'm going to get 3 minus 3, which is 0. So I know the dot product's 0. That means these guys have to be orthogonal. Let's look at 46. So I don't see a scalar multiple right off. So let's start with the dot product again. 4 times 1 half plus 3 times negative 2 over 3. So this is 2 minus 2. So once again, we're getting 0. That means orthogonal. So now let's look at 47. So once again, I'm not seeing a scalar multiple here. So just for fun, let's try that dot product. And let's see where that gets us. So I have negative 2/3 minus 8/3. So right off the bat, we see that that's definitely not equal to 0. So they are not orthogonal. And we could have also told that, seen that, because we had a negative times a positive plus a negative times a positive again. So we would have ended up with a negative number. So there's no way you'd get 0 if you're adding two negatives together. So now let's see if one is a scalar multiple. So let's say we have that vector 2, negative 4. Can we multiply by something? Can we multiply negative 1/3, 2/3 by something to get that 2, negative 4? So we're setting up this little mini system here. So 2 has to be equal to negative c over 3. And negative 4 has to be equal to 2c over 3. So if we were to solve this, we see c has to be negative 6. The question is, does that satisfy this equation? Well, let's see. And I'm just going to solve this. Negative 12 is equal to 2c. So I do get negative 6. Which means that if I were to multiply this fractional vector by negative 6, I will get that guy. So that 2, negative 4 is a scalar multiple of the vector negative 1/3, 2/3, which means this is definitely parallel. And then now let's look at 48. So I'm going to start with that dot product again. If I were to find that dot product, u dot v, I'm going to get 0 plus 1, which is definitely not 0. So we know they are not orthogonal. Now we have to check for parallel. So what we're asking is there a way I can multiply vector v by something so that I get vector u? You could also set it up the other way. Can I multiply u by something to get v? Either way, is there something that satisfies that? Can I multiply one by the other and get that? So let's see. 1 is equal to 0c. And then negative 1 is equal to negative 1c. Well, this guy's easy to solve. 1 has to be equal to c. But that doesn't work here, right? Because we have a 0 times c, which is a 0. So that tells us that there's no solution to this problem. Even though 1 worked for that second equation, if we were to plug 1 in here, it does not satisfy that second equation. So that means no solution, so not parallel. Since they're not orthogonal and they're not parallel, then these are neither. So these are neither parallel nor orthogonal. So 56 has a different flavor to it. We want to look at all vectors that are going to be orthogonal to this vector u. So to be orthogonal, the dot product has to be equal to 0. So we want u dotted with some vector v to be equal to 0. So let's set up a system of equations. So we need vector u dotted with v1, v2, v3 to be equal to 0. So we have 4v1 minus v2 plus 0 v3 is equal to 0. Now I'm going to solve this thing for v1. So v1 is equal to v2 divided by 4. And v2 can be anything. So here's what I'm going to do. I'm going to write this parametrically just a little bit nicer. I'm going to let v2 be equal to t, where t can be anything. And that means v1 has to be defined as 1/4 times our v2 value, which is t. So vectors that match this criteria, that will be orthogonal to this, will have this format. 1/4 t, t, and then zero. That third component would have to be 0. Actually, no, that third component can be anything. So that third component could be anything because 0 is in that first vector in that third component. And 0 times anything here would give us a 0. So t and s are just real numbers. So that's all we're going to talk about with dot products. I hope that refreshes your memory about how to use a dot product. Dot product is called a Euclidean inner product because it satisfies some criteria to be a Euclidean inner product. We're going to play with that definition a little bit more in the next section, but the dot product's a general Euclidean inner product that's used a lot, especially in physics. So now I want to talk about just a couple of different theorems. One of those is, if I go back to the previous page, Cauchy-Schwarz. So the Cauchy-Schwarz inequality says if u and v are vectors in Rn, then the absolute value of the dot product is less than or equal to the magnitude of u times the magnitude of v. So I just want to demonstrate what's going on here. Remember, the dot product is a scalar value, so we can take the absolute value of that scalar value. So if I find in 34 u dot v, I'm going to have -1 plus 0, which is -1. So then now I'm going to find the magnitude of u. Square root of -1 squared plus 0 squared, which is the square root of 1 plus 0, which is going to give us 1. And I'm going to find that magnitude of v, which is going to be the square root of 2. So Cauchy-Schwarz inequality says if I were to take the absolute value of u dot v, that's always going to be less than or equal to the product of the magnitudes. So we have 1, and 1 is definitely less than or equal to square root of 2. Cauchy-Schwarz inequality is usually used to prove things. So we're not going to do a lot with it, but it does come up if you read some of the proofs. The next one I want to talk about is the triangle inequality. So if u and v are vectors in Rn, then the sum of u plus v, and I take the magnitude of that sum, is going to be less than or equal to the sum of the magnitude of u plus the magnitude of v. So what's going on here, we could actually think about this in terms of triangles. So let's say we have two vectors in space, u and v. So if I have vector u and I add vector v, we find the magnitude of u, and that's just how long this side is. If we find the magnitude of v, that's how long this side is. Well, if I find the sum of u plus v, adding tip to tail, I start at u, I end at v. There's my u plus v vector. So what this says is that this vector has to be shorter than or equal to, usually going to be shorter than though, the sum of this side plus this side. That's what the triangle inequality is saying. So let's just verify that in number 58. We have vector -1 1 and vector 2 0. So if I find u plus v and add those two vectors together, I'm going to get the vector 1 1. So the magnitude of u plus v would be the square root of 2. The magnitude of u would be the square root of 2. And the magnitude of v would be the square root of 4 plus 0, which is the square root of 4, which is 2. So the triangle inequality says the sum of the two sides' length has to be less than or equal to the magnitude of u plus the magnitude of v. So we know square root of 2 is definitely going to be less than square root of 2 plus 2. Now, if u and v are orthogonal, then that means that dot product is going to be equal to 0. That's the definition of orthogonal. Then we kind of have an extension of the Pythagorean theorem, which says that u plus v's magnitude squared is equal to the magnitude of u squared plus the magnitude of v squared. Now this only works for two vectors that are orthogonal. So notice that. Now that also, if and only if, means it works forwards and backwards, right? So if this holds, then you also know it's orthogonal. So that's another way you could check for orthogonality. That's much harder than checking for a dot product, though. So let's just verify that holds for 61. So I'm going to find u plus v, which is 2 0. So the magnitude of u plus v is equal to the square root of 2 squared plus 0 squared. The magnitude of u is the square root of 2. And the magnitude of V is also the square root of 2. So the Pythagorean theorem says this. Substitute in what I know. Square root of 2, quantity squared is 2. And 2 plus 2 is definitely equal to 4. So that's just verifying that the Pythagorean theorem holds. Again, you usually see the triangle inequality, this version of the Pythagorean theorem, and the Cauchy-Schwarz inequality really improving different things. So I just want to mention that they're there and they're out there in case you run across them. So let's go back to that idea of a dot product. We can take any vector and we can really view it as a matrix. So if we have a vector that's written this way, we could view it as a column matrix where we have n rows and we have one column. Or if we wanted to, we could even view it as a row matrix. So we could view it in either way. Vectors and matrices kind of go hand in hand, which means all the properties for matrices also have to work for vectors. So, but for simplicity in this book, we're going to use this idea that if we write it this way, then we can view it as a column matrix. So that also means that we could rewrite this idea of dot product in terms of matrix multiplication. So if we wanted to find u dot v and we're viewing these as column vectors or column matrices, then u is an n by 1 matrix and v is an n by 1 matrix. But I can't just multiply u and v together because the dimensions don't match. However, if I were to think about this u as the transpose of u. So now I'm thinking about, instead of a column, I'm thinking about it as a row. The transpose of u would look like this. And now I have a 1 by n matrix. So I have a 1 by n matrix here. V is an n by 1 matrix. And we see that matrix multiplication would be defined, and that would give me just a plain old number. It would give me a 1 by 1 matrix, which we could view as a scalar value. So then if we were to use our definition of multiplication, we multiply those together, plus those, plus so on until we get to those. So let's look at 23. Now we know what the dot product is going to be just by applying our definition of a dot product, but I want to use that idea of matrix multiplication to view that. So we can view u as a row vector, and we can view v as a column vector. And if we were to multiply these together, and then those, you can see how we're going to get that same value. So we can view dot products and matrix multiplication pretty much in the same way. The last thing I want to talk about in this section are parallel, orthogonal, and neither again. But now, instead of putting numbers with it, we're putting functions with it. So let's look at 69. if we were to find u dot v, that's where we have to start. Or that's where it's easiest, I think, to start. We have cosine theta sine of theta minus sine of theta cosine of theta plus 0. And we know that's going to be 0, which means even though these functions, or excuse me, these vectors have functions in them, they are actually orthogonal. So we're kind of branching that idea of orthogonality out, not just to talk about vectors that are numeric, but now we're talking about vectors that have functions in them. If we look at 70, we have u dot v is negative sine squared minus cosine squared plus 0. So we want to know, what is that equal to? Well, we could factor out a negative from the sine squared and cosine squared. And sine squared plus cosine squared is equal to a 1. So this guy's actually equal to a negative 1, and that's not 0. So they are definitely not orthogonal. So then we ask, is there something I can multiply this guy by to get this guy? So in the beginning, it looks like you can multiply by negative 1, but the problem comes with that third component. I can't multiply 1 by negative 1 and get 0. So there's no way I can get 0 from that, which means they are not parallel. We could see that without ever setting up a system of equations. And since they're not parallel, not orthogonal, these are going to be neither. So this is the end of the review of dot products. In the next section, we're going to pick up talking about the formal definition of a Euclidean inner product. And then we're going to do some fun stuff with that. So fun things to come.